Hello Math 119 students. I have posted a handout on hypothesis testing errors on Canvas, so I'm going to go over the handout right now. So when we do a hypothesis test, first thing we do is we state our null and alternative hypotheses. Then we collect data, and based on the data we calculate our test statistic. And then based on the value of the test statistic, we make our decision: either reject the null hypothesis or fail to reject the null hypothesis. However, in reality, the null hypothesis will actually either be true or false. And then we make our decision. If we reject the null hypothesis, but the null hypothesis is actually false, that's a correct decision. However, we may reject the null hypothesis, and the null hypothesis may actually be true. We call that a type 1 error. And then the other decision we can make is failing to reject the null hypothesis. If we fail to reject the null hypothesis, and the null hypothesis is actually true, that would be a correct decision. But if we fail to reject the null hypothesis when the null hypothesis is actually false, we call that a type 2 error. Okay, and then these two types of errors we have, type 1 and type 2 errors, have probabilities associated with them. The probability of making a type 1 error, we call that alpha. And alpha is also called the level of significance of the hypothesis test. So if you recall, when you do a problem in the homework, the level of significance will be a given value. However, the level of significance is actually chosen by the statistician. And the most common level is 5%, but it could also be 10% or 1%. Those are also common levels for alpha. And you would think that making alpha as small as possible would be a good idea, because when you make alpha as small as possible, it's also the probability of making a type 1 error. So you'll be reducing the probability of making a type 1 error, which sounds like it would be a good thing. However, there's a problem with that. And the problem lies in the fact that the probability of making a type 2 error, we call that beta. And the problem lies in the fact that if we reduce alpha, beta will automatically increase. So if we reduce alpha, we'll be reducing the probability of making a type 1 error, but the probability of making a type 2 error, beta, will automatically increase. So it works kind of like this diagram here. Reducing alpha automatically increases beta. Increasing alpha will automatically decrease beta. So you kind of have to make a decision. Would you rather have a lower chance of making a type 1 error or a lower chance of making a type 2 error? And how do you decide which one is better? Well, it depends on the consequences of these two errors. So let's look at this example I have here, which will demonstrate what's the best level to select for alpha. So in this problem we have a hypothesis test, kind of a quality control test for bolts. The specifications call for that the bolts are supposed to be 1/2 inch diameter bolts. So we're doing a quality control hypothesis test here to see if the bolts differ significantly from the requirements. So the null hypothesis, if we did this test, would be that the bolts meet the specifications. The null hypothesis would be that the mean diameter does in fact equal 1/2 inch. Then the alternative hypothesis would be that the bolts do not meet the specifications, so they're not 1/2 inch. So that means they may be a little bit too small or a little bit too big, but they don't meet the specifications. So what would be the meaning of a type 1 error in this example? Well, if you recall, with a type 1 error, the meaning of that is that we reject the null hypothesis, but the null hypothesis is actually true. So if we rejected the null hypothesis, our conclusion would be that the bolts are defective. Right? Because we would be concluding that the mean diameter is not ½ inch, so the bolts are defective. That would be our conclusion. Okay, so we would conclude the bolts are defective since we rejected the null hypothesis. But actually, the null hypothesis is true. Actually, the bolts are good. So what would be the consequence of making a type 1 error for the company? The company that manufactures the bolts. Okay, well, if you think about it, the company would think that the bolts are defective, and so they would probably recalibrate their machines to make the bolts, and they may throw away bolts that are perfectly good, thinking that they're actually defective. So that would not be good for as far as the company is concerned. However, let's look at the type 2 error. So we'll see if the consequences for a type 2 error are even worse for the company than a type 1 error. So with a type 2 error, we failed to reject the null hypothesis, but the alternative hypothesis is actually true. So if we fail to reject the null hypothesis, we would conclude that the null hypothesis is true, which means we conclude the bolts are good. But actually, the alternative hypothesis is true. So the bolts are defective. Now, what would be the consequences for the company if they made a type 2 error? Well, let's think about that. The company would be sending out defective bolts thinking that they're actually good. Well, that doesn't sound very good, because if they sent out defective bolts, they could get sued. So I would think that a type 2 error would have more severe consequences than a type 1 error. So as far as the company is concerned anyway. Therefore, the company would like to reduce beta. So how can the company reduce beta? In order to reduce beta, they may want to slightly increase alpha. So let's say alpha is 0.05. They may want to increase alpha up to, let's say, 0.1, and that will reduce beta somewhat. So this gives you an idea of how, because in some cases, such as drug testing, you can have life or death consequences as far as certain drugs are concerned. So this gives you an idea on how alpha is determined depending on the consequences of the two types of errors. Now the last page I want to go over as well. Here's page 3 of the handout. You can maybe check out the elephant example. But one thing I wanted to mention on this page is we never say that we accept the null hypothesis. That's why we say we either reject the null hypothesis or we fail to reject the null hypothesis. We never say accept the null hypothesis. Okay? Because it's not the same as saying do not reject the null hypothesis. So a lack of evidence against the null hypothesis is not the same as evidence for the null hypothesis. And here's a quote from maybe the most famous statistician of all time, Ronald Fisher. So he gives you an explanation of why you don't want to say that you accept the null hypothesis here. I'll let you read this for yourself. And that's the end of this handout, or this video. So I hope it was helpful for you.